Welcome to Slothful Slumber, the podcast where we transform the vast knowledge of the internet into a gentle lullaby for your mind. I'm your host, Luna Dreamwell, and I'm here to guide you on a journey to tranquility through the soothing cadence of Wikipedia articles. Each episode will delve into the most wonderfully mundane and sleep-inducing topics, helping you drift off into a realm of serene dreams. So find your comfortable space, close your eyes, and let the dull hum of information carry you into a restful slumber. Now, let's embark on tonight's voyage of tranquil learning as we explore a topic so peacefully uneventful, it just might whisk you away to the land of dreams. This Wikipedia article is titled Biomechanics. Biomechanics is the study of the structure, function, and motion of the mechanical aspects of biological systems, at any level from whole organisms to organs, cells, and cell organelles, using the methods of mechanics. Biomechanics is a branch of biophysics. In 2022, computational mechanics goes far beyond pure mechanics and involves other physical actions: chemistry, heat and mass transfer, electric and magnetic stimuli, and many others. Etymology. The word biomechanics, 1899, and the related biomechanical, 1856, come from the ancient Greek bios, life, and mechanique, mechanics, to refer to the study of the mechanical principles of living organisms, particularly their movement and structure. Subfields. Biofluid mechanics. Biological fluid mechanics, or biofluid mechanics, is the study of both gas and liquid fluid flows in or around biological organisms. An often studied liquid biofluid problem is that of blood flow in the human cardiovascular system. Under certain mathematical circumstances, blood flow can be modeled by the Navier-Stokes equations. In vivo, whole blood is assumed to be an incompressible Newtonian fluid. However, this assumption fails when considering forward flow within arterioles. At the microscopic scale, the effects of individual red blood cells become significant, and whole blood can no longer be modeled as a continuum. When the diameter of the blood vessel is just slightly larger than the diameter of the red blood cell, the Furius-Lindquist effect occurs, and there is a decrease in wall shear stress. However, as the diameter of the blood vessel decreases further, the red blood cells have to squeeze through the vessel and often can only pass in a single file. In this case, the inverse Furius-Lindquist effect occurs and the wall shear stress increases. An example of a gaseous biofluids problem is that of human respiration. Recently, respiratory systems in insects have been studied for bioinspiration for designing improved microfluidic devices. Biotribology. Biotribology is the study of friction, wear, and lubrication of biological systems, especially human joints such as hips and knees. In general, these processes are studied in the context of contact mechanics and tribology. Additional aspects of biotribology include analysis of subsurface damage resulting from two surfaces coming in contact during motion, that is rubbing against each other, such as in the evaluation of tissue-engineered cartilage. Comparative biomechanics. Comparative biomechanics is the application of biomechanics to non-human organisms, whether used to gain greater insights into humans, as in physical anthropology, or into the functions, ecology, and adaptations of the organisms themselves. Common areas of investigation are animal locomotion and feeding, as these have strong connections to the organism's fitness and impose high mechanical demands. Animal locomotion has many manifestations, including running, jumping, and flying. Locomotion requires energy to overcome friction, drag, inertia, and gravity, though which factor predominates varies with environment. Comparative biomechanics overlaps strongly with many other fields, including ecology, neurobiology, developmental biology, ethology, and paleontology, to the extent of commonly publishing papers in the journals of these other fields. Comparative biomechanics is often applied in medicine with regards to common model organisms such as mice and rats, as well as in biomimetics, which looks to nature for solutions to engineering problems. Computational biomechanics. Computational biomechanics is the application of engineering computational tools, such as the finite element method, to study the mechanics of biological systems. Computational models and simulations are used to predict the relationship between parameters that are otherwise challenging to test experimentally, or used to design more relevant experiments, reducing the time and costs of experiments. Mechanical modeling using finite element analysis has been used to interpret the experimental observation of plant cell growth to understand how they differentiate, for instance. In medicine, over the past decade, the finite element method has become an established alternative to in vivo surgical assessment. One of the main advantages of computational biomechanics lies in its ability to determine the endo-anatomical response of an anatomy without being subject to ethical restrictions. This has led FE modeling, or other discretization techniques, to the point of becoming ubiquitous in several fields of biomechanics, while several projects have even adopted an open-source philosophy, for example, Biospine, and Sonics, as well as the SOFA, Phoenix Frameworks, and Phibio. Computational biomechanics is an essential ingredient in surgical simulation, which is used for surgical planning, assistance, and training. In this case, numerical discretization methods are used to compute, as fast as possible, the response of a system to boundary conditions, such as forces, heat and mass transfer, electrical and magnetic stimuli. Experimental biomechanics. Experimental biomechanics is the application of experiments and measurements in biomechanics. Continuum biomechanics. The mechanical analysis of biomaterials and biofluids is usually carried forth with the concepts of continuum mechanics. This assumption breaks down when the length scales of interest approach the order of the microstructural details of the material. One of the most remarkable characteristics of biomaterials is their hierarchical structure. In other words, the mechanical characteristics of these materials rely on physical phenomena occurring in multiple levels, from the molecular all the way up to the tissue and organ levels. Biomaterials are classified in two groups, hard and soft tissues. Mechanical deformation of hard tissues, like wood, shell, and bone, may be analyzed with the theory of linear elasticity. On the other hand, soft tissues, like skin, tendon, muscle, and cartilage, usually undergo large deformations, and thus their analysis rely on the finite strain theory and computer simulations. The interest in continuum biomechanics is spurred by the need for realism in the development of medical simulation. Plant biomechanics. The application of biomechanical principles to plants, plant organs, and cells has developed into the subfield of plant biomechanics. Application of biomechanics for plants ranges from studying the resilience of crops to environmental stress to development and morphogenesis at cell and tissue scale, overlapping with mechanobiology. Sports biomechanics. In sports biomechanics, the laws of mechanics are applied to human movement in order to gain a greater understanding of athletic performance and to reduce sport injuries as well. It focuses on the application of the scientific principles of mechanical physics to understand movements of action of human bodies and sports, implements such as cricket bat, hockey stick, and javelin, etc. Elements of mechanical engineering, for example, strain gauges. Electrical engineering, for example, digital filtering. Computer science, for example, numerical methods. Gait analysis, for example, force platforms. And clinical neurophysiology, for example, surface EMG, are common methods used in sports biomechanics. Biomechanics in sports can be stated as the muscular, joint, and skeletal actions of the body during the execution of a given task, skill, and/or technique. Proper understanding of biomechanics relating to sports skill has the greatest implications on sports performance, rehabilitation, and injury prevention, along with sport mastery. As noted by Dr. Michael Yesis, one could say that best athlete is the one that executes his or her skill the best. Vascular biomechanics. The main topics of the vascular biomechanics is the description of the mechanical behavior of vascular tissues. It is well known that cardiovascular disease is the leading cause of death worldwide. Vascular system in the human body is the main component that is supposed to maintain pressure and allow for blood flow and chemical exchanges. Studying the mechanical properties of this complex tissues improves the possibility to better understanding cardiovascular diseases and drastically improve personalized medicine. Vascular tissues are inhomogeneous with a strongly nonlinear behavior. Generally, this study involves complex geometry with intricate load conditions and material properties. The correct description of these mechanisms is based on the study of physiology and biological interaction. Therefore, it is necessary to study wall mechanics and hemodynamics with their interaction. It is also necessary to premise that the vascular wall is a dynamic structure in continuous evolution. This evolution directly follows the chemical and mechanical environment in which the tissues are immersed, like wall shear stress or biochemical signaling. History. Antiquity. Aristotle, a student of Plato, can be considered the first biomechanic because of his work with animal anatomy. Aristotle wrote the first book on the motion of animals, De Motu Animalium, or on the movement of animals. He saw animals' bodies as mechanical systems, pursued questions such as the physiological difference between imagining performing an action and actual performance. In another work, On the Parts of Animals, he provided an accurate description of how the ureter uses peristalsis to carry urine from the kidneys to the bladder. With the rise of the Roman Empire, technology became more popular than philosophy, and the next biomechanic arose. Galen, 129 AD to 210 AD, physician to Marcus Aurelius, wrote his famous work On the Function of the Parts about the human body. This would be the world's standard medical book for the next 1,400 years. Renaissance. The next major biomechanic would not be around until the 1490s, with the studies of human anatomy and biomechanics by Leonardo da Vinci. He had a great understanding of science and mechanics and studied anatomy in a mechanics context. He analyzed muscle forces and movements and studied joint functions. These studies could be considered studies in the realm of biomechanics. Leonardo da Vinci studied anatomy in the context of mechanics. He analyzed muscle forces as acting along lines, connecting origins and insertions, and studied joint function. Da Vinci is also known for mimicking some animal features in his machines. For example, he studied the flight of birds to find means by which humans could fly. And because horses were the principal source of mechanical power in that time, he studied their muscular systems to design machines that would better benefit from the forces applied by this animal. In 1543, Galen's work on the function of the parts was challenged by Andreas Vesalius at the age of 29. Vesalius published his own work called On the Structure of the Human Body. In this work, Vesalius corrected many errors made by Galen, which would not be globally accepted for many centuries. With the death of Copernicus came a new desire to understand and learn about the world around people and how it works. On his deathbed, he published his work on the revolutions of the heavenly spheres. This work not only revolutionized science and physics, but also the development of mechanics and later biomechanics. Galileo Galilei, the father of mechanics and part-time biomechanic, was born 21 years after the death of Copernicus. Over his years of science, Galileo made a lot of biomechanical aspects known. For example, he discovered that animals' masses increase disproportionately to their size, and their bones must consequently also disproportionately increase in girth, adapting to load-bearing rather than mere size. The bending strength of a tubular structure, such as a bone, is increased relative to its weight by making it hollow and increasing its diameter. Marine animals can be larger than terrestrial animals because the water's buoyancy relieves their tissues of weight. Galileo Galilei was interested in the strength of bones and suggested that bones are hollow because this affords maximum strength with minimum weight. He noted that animals' bone masses increased disproportionately to their size. Consequently, bones must also increase disproportionately in girth rather than mere size. This is because the bending strength of a tubular structure, such as a bone, is much more efficient relative to its weight. Mason suggests that this insight was one of the first grasps of the principles of biological optimization. In the 17th century, Descartes suggested a philosophic system whereby all living systems, including the human body, but not the soul, are simply machines ruled by the same mechanical laws, an idea that did much to promote and sustain biomechanical study. Industrial era. The next major biomechanic, Giovanni Alfonso Borelli, embraced Descartes' mechanical philosophy and studied walking, running, jumping, the flight of birds, the swimming of fish, and even the piston action of the heart within a mechanical framework. He could determine the position of the human center of gravity, calculate and measure inspired and expired air volumes, and he showed that inspiration is muscle-driven and expiration is due to tissue elasticity. Borelli was the first to understand that the levers of the musculature system magnify motion rather than force, so that muscles must produce much larger forces than those resisting the motion. Influenced by the work of Galileo, whom he personally knew, he had an intuitive understanding of static equilibrium in various joints of the human body well before Newton published the laws of motion. His work is often considered the most important in the history of biomechanics because he made so many new discoveries that opened the way for the future generations to continue his work and studies. It was many years after Borelli before the field of biomechanics made any major leaps. After that time, more and more scientists took to learning about the human body and its functions. There are not many notable scientists from the 19th or 20th century in biomechanics, because the field is far too vast now to attribute one thing to one person. However, the field is continuing to grow every year and continues to make advances in discovering more about the human body. Because the field became so popular, many institutions and labs have opened over the last century, and people continue doing research. With the creation of the American Society of Biomechanics in 1977, the field continues to grow and make many new discoveries. In the 19th century, Étienne Jules Marais used cinematography to scientifically investigate locomotion. He opened the field of modern motion analysis by being the first to correlate ground reaction forces with movement. In Germany, the brothers Ernst Heinrich Weber and Wilhelm Eduard Weber hypothesized a great deal about human gait, but it was Christian Wilhelm Braun who significantly advanced the science using recent advances in engineering mechanics. During the same period, the engineering mechanics of materials began to flourish in France and Germany under the demands of the Industrial Revolution. This led to the rebirth of bone biomechanics when the railroad engineer Carl Coleman and the anatomist Hermann von Meyer compared the stress patterns in a human femur with those in a similarly shaped crane. Inspired by this finding, Julius Wolff proposed the famous Wolff's law of bone remodeling. Applications. The study of biomechanics ranges from the inner workings of a cell to the movement and development of limbs, to the mechanical properties of soft tissue and bones. Some simple examples of biomechanics research include the investigation of the forces that act on limbs, the aerodynamics of bird and insect flight, the hydrodynamics of swimming in fish, and locomotion in general across all forms of life, from individual cells to whole organisms. With growing understanding of the physiological behavior of living tissues, researchers are able to advance the field of tissue engineering, as well as develop improved treatments for a wide array of pathologies, including cancer. Biomechanics is also applied to studying human musculoskeletal systems. Such research utilizes force platforms to study human ground reaction forces and infrared videography to capture the trajectories of markers attached to the human body to study human 3D motion. Research also applies electromyography to study muscle activation, investigating muscle responses to external forces and perturbations. Biomechanics is widely used in orthopedic industry to design orthopedic implants for human joints, dental parts, external fixations, and other medical purposes. Biotribology is a very important part of it. It is a study of the performance and function of biomaterials used for orthopedic implants. It plays a vital role to improve the design and produce successful biomaterials for medical and clinical purposes. One such example is in tissue-engineered cartilage. The dynamic loading of joints considered as impact is discussed in detail by Emanuel Willert. It is also tied to the field of engineering because it often uses traditional engineering sciences to analyze biological systems. Some simple applications of Newtonian mechanics and/or material sciences can supply correct approximations to the mechanics of many biological systems. Applied mechanics, most notably mechanical engineering disciplines such as continuum mechanics, mechanism analysis, structural analysis, kinematics, and dynamics, play prominent roles in the study of biomechanics. Usually, biological systems are much more complex than man-built systems. Numerical methods are hence applied in almost every biomechanical study. Research is done in an iterative process of hypothesis and verification, including several steps of modeling, computer simulation, and experimental measurements.